Hello, everyone. My name is Erlihson, and I'm going to talk about generation of any visual data with text-to-image diffusion models. I also like to thank the previous speaker about providing a required background about diffusion models. I also will talk about work of the previous speaker team in my presentation, and let's start. Oh, sorry. Okay. This is the outline of my lecture. I will provide a really quick background about the noisy and diffusion probabilistic models, the DPMs, or just DMs. Next, I'll discuss briefly popular text-to-image diffusion models like Imagine, DALI 2, Stable Diffusion. Then I will present four broad approaches to leverage text-to-image diffusion models to generate visual data. And then I will explain how we can harness text-to-image diffusion models to create video, to edit images and video. We can also use diffusion models for editing, for building and editing 3D models, point clouds. And I will also talk how we can add more capabilities to diffusion models. For example, capability to receive edges and segmentation and depth maps and build images based on that. Will be more convenient. Okay. My name is Mike Erlihson. I'm principal data scientist in a cyber company called South Security. I'm also a founder of DeepNet Learners. We are reviewing, probably you know this community projects. We are reviewing deep learning papers in Hebrew. My collaborators and me, we wrote about 17, maybe a bit more reviews. And I also co-author of Machine and Deep Learning in Hebrew book. Okay, so you're probably here, if you are working in generative AI, you probably heard about diffusion models. In the pretty all generative models are now featured by diffusion models. Before 3 or 4 years, it was GANs and variation autoencoder. Now we have diffusion models, and we just using their power to generate many types of visual content. Okay, but let's understand how did it start. This is this paper called Diffusion Models Beat GANs on image synthesis. It was released in its last version was released in June 2021, 2 years ago. And this is the first paper which claimed that they developed a diffusion model, the DPM. It just exhibited better performance than state-of-the-art GANs. And here, in this moment, we started to see many diffusion models capable of generating many types of visual data. Okay, so and as I already told, this paper started in a race in the computer vision community, and the race was to develop the diffusion model powered models across actually all domains and tasks. They have video generation and 3D models and point clouds and image and video editing, and there are also not generative tasks just like object detection and the different types of segmentation, which diffusion models are used to deliver great results. Then super cool diffusion DM powered models started popping up. You are probably familiar with DALI 2, Imagine, Stable Diffusion, Midjourney, and the results were just amazing. You probably saw these pictures many times. For example, DALI, here you see this cute dolphin. You can see that the quality of this picture is really high, the resolution is really high, and it's and it really fits its textual description. When they have imagine, we have which was capable of building of generating images from quite a long textual description. Here the results are just very high quality. Then we have a stable diffusion by Stability AI, and the stable diffusion just accelerated the time which is needed to generate to generate images. I will explain about how it works in my next slides. But now the question is, we saw some diffusion models which are capable of generating images, but now the question is, can we utilize these very powerful diffusion models to generate other types of visual content? And the answer is yes. And as I already mentioned, we can utilize these diffusion models to generate 3D models and to generate video and perform image and video editing and personalization. We can even use it for semantic segmentation and object detection. Okay. Next, we will discuss very briefly diffusion models, how it works. I will start from the very simple sketch of what is generative model. Generative model is a very simple model. They have very simple distribution, for example, Gaussian distribution. And what is generative model? Generative model is just a map from this simple distribution into our data distribution. So here they have a simple distribution from the left and the more complicated distribution from the right. And then you train your diffusion, when you train your generative model, you just train the mapping between simple distribution you can easily sample from. And this map just generates you samples from more complex distribution. The same happens when your data is multidimensional. You just start from Gaussian noise, and then you just learn the mapping. You just train the model to generate samples from your data set. You train your model on the data set, and then you just train your model to create samples from this data set. Okay. So what is diffusion model? A previous speaker just provided this required background. I will explain it very briefly. There are two processes in the diffusion model: the forward process and the backward process. And in the course of forward process, we just destroying the data by gradually adding a small amount of Gaussian noise, and then we train the model to reverse that process. Actually, to denoise the data, and in each step, we try to recreate, to build the content of the previous iteration. And how this is look like? Here we see a forward diffusion process. Here we see a generative reverse denoising process. And once we train our diffusion model to model the reverse process, we can just feed random Gaussian noise, and now we have a capability to generate new pieces of data. For example, these cute dogs. Okay. Next, we discuss briefly text-to-image diffusion models, model architecture. There are two main types of architecture. Here we see the DALI 2 architecture. Here we see imagine and stable diffusion. And the first architecture type, which was used by Imagine and DALI 2, first we use large language model or text encoder to encode the text in some embedding space. Then we train another model, which can be diffusion model, it can be other types of models, to create an image embedding from this text embedding. This part is optional. You can do it, you cannot do it. You can create your picture from the texture, from the embedding of your text as well. And then this text embedding or this image embedding, we use it as an input to our text-to-image diffusion models, and the output of this model is actually an image. Now, the second architecture type is Very simple. They actually train, they actually perform diffusion, we actually train diffusion model in the embedding space. In the previous approach, we just train a diffusion model in the pixel space, and it can be slow. So here the main approach is to train a diffusion model in the embedding space. So here we train an image encoder and decoder, which in the case of stable diffusion was the VQ-GAN based, and also text encoder. Then we train a diffusion model to build the representation of the image in the embedding space, and then we just decode it by our decoder to generate an image. And as it is this approach is can generate your pictures very fast compared to the previous approaches. Okay, now let's talk about how can we utilize the diffusion text-to-image diffusion models to train to create different types of visual data. There are four main approaches to do it. The first approach is a modify output or format of diffusion models, and here we can think about video creation. Instead of creating images, we just train diffusion models which create frames of video. Next is fine-tuning diffusion models, or just choosing or optimizing tokens for your objects, and the previous speaker just talked about it. And we can use it, for example, to generate images of your specific dog and car or watch. The third approach is to use pre-trained diffusion models to control or backpropagate the quality or alignment of visual models or projection with the textual description. Here, we don't touch diffusion models. Diffusion models is a type of critic here. And this approach is used in many papers which try to leverage diffusion models to build 3D models and point clouds. And the last approach is the adaptation of pre-trained diffusion models to receive input of different types. For example, you can train diffusion models to embed canny edges, outlines, and user scribbles. I will talk about it. Okay. Here you see the make a video. This is a paper of a year ago, I think. And here we are just changing the output format of our diffusion models, of our pre-trained text-to-image diffusion model. As I already mentioned, instead of creating a single image, we create a sequence of images, and then we just turn this sequence of images to video. Not every sequence of images is video, and the purpose of this model is just to convert the sequence of images, which for a given text description, to a video which looks like a video. Here is a very similar approach of creating video. Now note we have 7 super resolution text-to-image diffusion models, which are sometimes trained simultaneously, sometimes separately. We start from creating low resolution and low frame per second rate, and then we are gradually increasing the frame rate, increasing the resolution of these frames in order to get a video of a good quality. Next, we have a personalization. I think I can skip these slides because the previous speaker discussed it. So I will briefly discuss what it is done here. Here, we just choosing tokens for object. We are optimizing over the token space, and while keeping the text-to-image diffusion model frozen, and which enables us to get our diffusion models to create images of our own object, dog, car, watch. The second approach here is to fine-tune text-to-image diffusion model for your object. This is a great paper called Dream Booth, quite a popular paper. You have several images of a dog, and then it do actually the same personalization. It just creates the images of this specific object. Here we're just representing our object is so-called rare tokens, and then they fine-tune diffusion models and they try to preserve the semantic prior of the general object type, meaning that our diffusion models have a very strong capability, very strong alignment between textual and the image embeddings. So we try to cause it to create images of our objects while not destroying its these capabilities. And so we fine-tune diffusion models, and we also try to keep this semantic power of diffusion models as well. Okay, in this approach, we are not just fine-tuning only the large language model on a test encoder. We're fine-tuning them together. Actually, this approach just enables us to do image editing. Here you see this bird, and then in the image on the right, the bird is spreading wings. Pretty cool paper. And as already mentioned, this paper just fine-tunes LLM and fine-tunes pre-trained diffusion model as well. And here I was talking about video. I was talking about video generation, and this cool paper called DreamX just fused the approaches already I was talking about to actually enable diffusion models to edit video or to create video from a series of input images. Here we have 4 images, and you give a textual description. A toy farmer is lifting weights, and here the model creates a video in accordance with this textual description. Okay, now let's go to the point clouds, to 3D models. Point cloud is a way to describe an object, and this is a cool paper called Point E, leverages pre-trained text-to-image diffusion models to create point clouds of different objects for a given textual description. It starts from fine-tuning glide model, which is a well-known diffusion model, when it creates another diffusion models which creates a point cloud of this object according to its description in a low resolution, and then they train a super resolution diffusion model in order to get a point cloud with the high resolution. Okay, we also can use text-to-image diffusion models to evaluate or backprobe error of models of different types. Here we have a NERF. NERF is a neural field approach, and this is a way to characterize 3D models. And here we use diffusion models in order to assess quality of the NERF model we are generating. For example, we have here a NERF model, then it generates for a given NERF model, we generate a projection of this NERF model, and then we actually leverage a frozen text-to-image diffusion models in order to check how whether this model is good, how does it fit this textual description. So if and here you can see that the diffusion model is frozen. We are updating only the NERF. We are updating only the model which creates a 3D model of our object. Here this is a very similar work which creates a 3D model from a textual description. It do it in a latent space, and do, as you can see, do really cool stuff. It not just creates a 3D model for a given textual description, but it also do it for a given shape or for a given texture, as you can see on the image from the right. Here we can see it is a different paper, but do very similar thing. And the reason that I'm giving two papers are doing the same, which is very active area of research. After I completed composing this slide set, I saw at least 3 papers in 5 days, which are doing very similar stuff. Okay, and this is a very cool stuff. Instruct 3D to 2D, which is text interaction guided 3D to 3D conversion. So we have a 3D model of some object, and then they give a textual description, how we want to edit it. And the result is the new diffusion models, which fit to its description. For example, here we have this tractor, and then we just call the model, make it chocolate. And you have here a very cute 3D model of the chocolate tractor. And you can see some cool pictures here. For example, here you have this chair, and you just ask the model, what if it was made of paper? And it is quite cool. They use a similar approach, but instead of plain text-to-image diffusion models, which just creates an image from a textual description, here we have Instruct Fix-to-Fix diffusion model. What is Instruct Fix-to-Fix diffusion model? For a given picture and for a given textual description, it edits its picture in order to fit the description you give it. So here we have a 3D model of our source object, and then we are checking our target model, which is also 3D nerf model of the object, and then we just project it on some plane, and then we just use Instruct Fix-to-Fix model to check the quality of what we did. For example, here you just created this tractor from chocolate, and then you use Instruct Fix-to-Fix model to check whether the projection of this modified 3D model fits the source image of a tractor, and this textual instruction make it chocolate. And here it is important that this text-to-image model are frozen. It is not fine-tuned, and it is just a critique. This model is just used to help building this target 3D model. Okay. Now we are going to talk about ControlNet. It's a quite famous paper which appeared a couple of months, maybe 3 months ago. And this paper is really cool. I really love this paper. And what this paper did, it just adapted the diffusion models to receive input of different type. What's a different type? It can be canny edges, it can be half lines, it can be user scribbles, segmentation maps, depth maps. Actually, pretty all you can do to the pictures, you can train diffusion model on. I give some example. For example, here you get the canny edges, and then you ask the diffusion model to draw a man with beard sitting with 2 children. Or here we have some user scribbles of some turtle, and you ask the diffusion model to draw you a turtle in river, and the quality is very high. So how did they do it? At the first stage, they just trained a task-specific text-to-image model to learn additional control. One of the main difficulties here is just to learn to cause the diffusion model to embed this information like canny edges or user scribbles or segmentation map, to embed it in a similar in the same embedding space as you embed in your image and as you embed your text. So the first stage, you just train diffusion model to embed this information from a user to the embedding space, and then the next space you just combine this text-specific diffusion model to something that I invented, zero convolution. It is very simple neural net, and then you just combine this capability of embed to embed user information to the same embedding space as the image. You just combine to the frozen text-to-image model to create very cool stuff that they see in the saw on the previous slide. Okay, so what we learned today? We learned what is the noise and diffusion probabilistic models. Then we briefly discussed the two main text-to-image diffusion model architecture. Then we discussed the four broad approaches, how we can harness text-to-image diffusion models to build new types of data. And here you can see the not full list of the tasks which we can use text-to-image diffusion models. We can use it to image editing, personalization, video generation, 3D models, point clouds. We can use it to build images which fit a scribble given by user, depth maps, half lines. And I want to add that that this list is not full. We can use diffusion models pretty for every task in the visual domain. I saw a paper which were using diffusion models for panoptic segmentation and for object detection, and it is not limited for the visual domain. There are many applications of diffusion models in biology, in genetic research. So diffusion models is a really very powerful tool. Now I'm done. Thank you for your attention.